Sorry for the delay in getting the rest of the video done. Now let's move on to the stochastic gradient descent portion of the exam. So we're given this implementation of stochastic gradient descent. And if you look at the textbook, this is actually mini batch stochastic gradient descent. Okay, so the main difference between the two is in regular stochastic gradient descent, we evaluate the gradient at some random point, right? As opposed to in regular gradient descent, we evaluate the average gradient across all of the points in our training set. So in stochastic gradient descent, we evaluate the gradient at just one random test point because it's just much computationally simpler, right? In mini batch gradient descent, what we do is we pick some random subset of our points at each step in our iteration and evaluate the gradient on that random subset of points. Okay, so not often do they differentiate between stochastic gradient descent and mini batch stochastic gradient descent, but that's sort of what's going on here. Okay, so firstly, which of the following best describes the bug in how our data are sampled? And the correct option is the second one. Okay, so if you see what's going on here, if we look at line 16, we select our choice of indices before jumping into the for loop. Okay, so before we start iterating, what we do is suppose there are y points that we're dealing with. What we do is we randomly sample batch size numbers between 0 and y without replacement. And those will be the random indices that we use to calculate our gradient. So that's okay. But the issue is we're not creating these indices on each iteration. We're only picking these random indices once and sticking with that throughout our iteration. So the batch is essentially constant throughout our iteration, when what it's supposed to be is the batch is randomly reshuffled in each of our iterations. Okay, so this line where we're creating what the indices are should actually be inside the for loop. Okay, so again, the issue is upon each iteration, we're supposed to resample our indices again, and that's not what's happening here. So in this case, once our indices are chosen, they're not really changing. Okay, so that's not exactly what mini batch stochastic gradient descent does. In B, assuming that the stochastic gradient grad is computed correctly, what is the correct implementation of the gradient update? So recall, the gradient descent update equation looks something like theta at time step t plus 1 is theta at time step t minus alpha, where alpha is our step size, times our gradient, okay, of our loss function, okay? And so right off the bat, we can get rid of two of our options, okay? We can get rid of the third one because there we're adding something times our gradient, which is not what we want. And we can get rid of the first option because we're dividing by our gradient instead of multiplying by the gradient. So that's also not quite right. So that leaves us with the second option or the fourth option. So it turns out the correct answer is the fourth option, and here's why. So as time goes on, as we pass through more and more iterations, our step size will probably decrease, right? Because the more iterations we've gone through, we're likely closer to our optimal value that we're trying to find. And so we want our changes in our estimate of theta to decrease, right? What the second option is saying is our step size is increasing as time goes on. And why is that? Well, because t ranges between 1 and whatever max iterations is, right? So suppose we want 10,000 iterations. On the 10,000th iteration, we're going to be moving 10,000 units times whatever our gradient is. So we're never going to converge like that, right? For this to work, our step size has to be decreasing or at least not increasing, right? And so that's why the fourth option is correct, because 1 over t, of course, decreases as t increases, and t will range between 1 and whatever our maximum iterations is. So in order for this to converge, the correct option is 1 over t times gradient. Okay, C, suppose we wanted to add L2 regularization, with each dimension having a different regularization parameter. Which of the following rewrites line 20 so that we achieve this goal? Okay, so now essentially what we need to do is add the gradient of our regularization function to the old gradient. Okay, so essentially we need to be adding something here. Okay, and so notice our regularization function just looks like lambda 1 theta 1 squared plus lambda 2 theta 2 squared plus dot 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 dot. And if we take the partial derivative of our regularization function with respect to theta 1, we'll get 2 lambda theta 1, right? So if we take the partial of r with respect to theta 1, we'll get 2 lambda 1 theta 1, because the rest of it is a constant with respect to theta 1. We do that with respect to theta 2, we'll get 2 lambda 2 theta 2, so on and so forth. So generalizing this, the gradient of our regularization function is 2 times theta times lambda. Okay? And that corresponds to the first option. And so that's how we would rewrite the above to incorporate L2 regularization. Now lastly, 35, use the following plot to answer each of the following questions about convexity. Firstly, f1 of x, which is equal to the max of 0.01x and negative x, is convex. So that's true. And let's look at why. Okay, so again, the definition of convexity that will probably help us the most in this diagram is trying to see if every possible secant line we draw on the function will be on or above the function. Okay, so there are 3 possibilities if we're looking at f1 of x, right? Either the 2 points we choose are on the left side of the function, which that secant line is indeed on or above the function. The 2 could be on the right side, which again, they're on or above the function. Or one can be on the left side and one can be on the right side. And again, that was a very bad line, but you know, that is on or above the function. So in all 3 cases, any secant line will be on or above the function. So we say f1 of x is convex. 2 is f2 of x is equal to negative 2x. Is that convex? Yes, because again, all lines of the form y is equal to mx plus b are convex, because if you pick any 2 points on the line, it will be on or above the function. And specifically in this case, it will be on the function. Okay, so that is true. Okay, is f3 of x, which is equal to negative x squared, convex? No, it's not, because clearly you can see here, if I pick 2 points on the curve and draw the secant between them, it is below the function, not on or above. Right, so that's false. Okay, you don't even really need to have the picture to know that, because x squared is known to be convex, so negative x squared will not be convex. Okay, and lastly, f4 of x is equal to the sum of f1 of x and f2 of x. Is that convex? Yes, because the sum of 2 convex functions is also convex. Okay, and we won't go over a proof of that right now, but we know that f1 of x is convex and f2 of x is convex. So when we sum them, that should also be convex. Okay, so that wraps up the stochastic gradient descent and convexity portion of the exam.